Imagine you're playing a cosmic game of pool, but instead of solid and striped balls, you've got planets and stars. Now, if you're dealing with just two celestial bodies, like Earth orbiting the Sun, it's pretty straightforward. You can predict their dance with pinpoint accuracy using some nifty equations. But throw in a third body and suddenly the universe throws you a curveball. Welcome to the mind-bending world of the three-body problem. So what exactly is this cosmic conundrum that's been giving scientists headaches for centuries? Assume you have three celestial bodies, like stars or planets, all pulling on each other with their gravitational forces. Sounds simple, right? Wrong. This seemingly innocent setup creates a mathematical puzzle so complex that it stumped some of the greatest minds in history. The three-body problem isn't just some abstract concept cooked up by bored mathematicians. It's a fundamental challenge in understanding how our universe works. Think about our solar system. Sure, we mostly focus on Earth's relationship with the Sun, but what about when the Moon joins the party? Or when Jupiter's massive gravity tugs on a passing asteroid? Suddenly, we're in three-body territory and things get weird. Now you might be wondering, why is this such a big deal? We've sent rockets to Mars and probes to the edge of the solar system. Surely we've got this figured out. Well, here's the kicker. We don't. At least, not entirely. The two-body problem? Piece of cake. Sir Isaac Newton cracked that one back in the 17th century. But add just one more body and our neat and tidy equations go out the window. Let's break it down a bit. In a two-body system, like a planet orbiting a star, we can predict the motion with incredible accuracy. It's like a cosmic waltz, with each partner always knowing exactly where the other will be. But introduce a third dancer and suddenly it's less waltz and more like a chaotic mosh pit. The movements become incredibly sensitive to the tiniest changes. A nudge here, a slight shift there, and boom, your predicted orbit goes wildly off course. This sensitivity is what makes the three-body problem so devilishly difficult. It's not just hard, it's fundamentally unpredictable in many cases. We're talking about a level of chaos that would make a butterfly effect look like a gentle breeze. And it's this chaotic nature that has fascinated scientists and mathematicians for centuries. But why should you care about some esoteric problem in celestial mechanics? Well, buckle up, because the three-body problem has implications that stretch far beyond the realm of astronomy. This seemingly simple puzzle has been a driving force behind some of the most groundbreaking developments in mathematics and physics. Take chaos theory, for instance. You know that branch of mathematics that gave us cool fractal patterns and the idea that a butterfly flapping its wings in Brazil could cause a tornado in Texas? The three-body problem was one of the key inspirations for the development of chaos theory. It showed us that even simple, deterministic systems could produce wildly unpredictable results. And it's not just theoretical. Understanding the three-body problem has practical applications in everything from planning space missions to predicting the long-term stability of our solar system. Want to park a satellite at a Lagrange point where the gravitational forces of the Earth and Moon balance out? You're dealing with a three-body problem. Curious about whether an asteroid might smash into Earth millions of years from now? Yep. Three-body problem again. But here's where it gets really mind-bending. The three-body problem isn't just difficult, it's actually impossible to solve completely in the general case. That's right, impossible. As in, no matter how smart you are or how powerful your supercomputer is, you can't come up with a single, neat equation that will predict the motions of three interacting bodies for all possible starting conditions. Now, before you throw your hands up in despair and declare celestial mechanics a lost cause, there's good news. While we can't solve the general three-body problem, we can tackle specific cases. Scientists and mathematicians have developed all sorts of clever approximations and numerical methods to deal with three-body scenarios. It's like we can't see the whole picture, but we can get pretty good glimpses of parts of it. And sometimes those glimpses reveal absolutely stunning patterns. There are certain initial conditions where three bodies can dance in stable, repeating orbits. Picture three stars chasing each other in a figure-8 pattern, or two small bodies whirling around a larger one in a perfectly choreographed cosmic ballet. These special solutions are like finding nuggets of order in a sea of chaos. But even with these special cases and approximations, the three-body problem remains a frontier of human knowledge. It's a humbling reminder that even in our age of incredible scientific and technological advancement, there are still fundamental questions about the universe that we can't fully answer. It's a problem that bridges the gap between the clockwork precision of Newtonian physics and the weird, wild world of chaos and complexity. So we've dipped our toes into the cosmic waters of the three-body problem. But now it's time to dive deep into the swirling vortex of its complexities. Buckle up, because things are about to get mind-bendingly chaotic. Remember how we said that adding just one more body to our celestial dance turns a waltz into a mosh pit? Well, let's break down why exactly this happens. In a two-body system, we're dealing with a straightforward tug-of-war between two objects. Their gravitational pull on each other creates predictable elliptical orbits. It's like a cosmic game of catch. You always know where the ball is going to end up. But throw in a third body, and suddenly it's like playing catch in a hurricane while riding a roller coaster. Each body is now pulling on the other two, and those forces are constantly changing as the bodies move. It's a feedback loop of gravitational chaos. The motion of each body affects the others, which in turn affects the first body, which then changes how it affects the others. You get the idea. It's enough to make your head spin faster than a pulsar. The interdependence is what mathematicians call the coupled system. And in the case of the three-body problem, it's a non-linear coupled system, which is a fancy way of saying really complicated. The equations that describe the motion of these bodies are so intertwined and sensitive that even the tiniest change in initial conditions can lead to wildly different outcomes. Do you know conceptual or mathematical problems that make the world's geniuses want to pull their hairs off? I'd love to hear about them in the comments below. Imagine you're playing a game of pool where the balls are magnets. Not only do you have to account for how hard you hit the cue ball and at what angle, but also how each ball's magnetic field will affect the others as they move. Oh, and the table is constantly shifting and warping. That's the kind of complexity we're dealing with in the three-body problem. Now, you might be thinking, surely with our modern supercomputers and advanced algorithms, we can crunch the numbers and figure this out, right? Well, yes and no. We can certainly use numerical methods to simulate three-body systems and make pretty accurate short-term predictions. But here's the kicker. Because of the chaotic nature of the system, our ability to predict long-term behavior is severely limited. This limitation isn't just a matter of not having fast enough computers or smart enough mathematicians. It's a fundamental property of chaotic systems. Even if we could measure the initial positions and velocities of the bodies with infinite precision, which we can't, and even if we could compute with infinite accuracy, which we also can't, we still couldn't predict their positions arbitrarily far into the future. The system is just too sensitive to tiny perturbations. But don't despair. The fact that we can't solve the general three-body problem doesn't mean we're completely in the dark. Scientists and mathematicians have developed a whole toolkit of techniques to tackle specific cases and gain insights into the behavior of these systems. One approach is to look for special cases where the three bodies move in stable, periodic orbits. These are like islands of order in a sea of chaos. The most famous of these is probably the Lagrange points, specific locations where a small object can maintain a stable position relative to two larger bodies. We use these points for parking satellites and space telescopes. Another technique is perturbation theory, where we start with a simpler, solvable problem, like the two-body problem, and then add in the effects of the third body as small perturbations. This works well when one body is much smaller than the other two, like when we're calculating the motion of a spacecraft influenced by both Earth and the Moon. We can also use numerical integration methods to simulate the motion of three-body systems on computers. While these simulations can't predict the long-term future with certainty, they can give us valuable insights into the overall behavior of the system and help us identify interesting patterns and possibilities. And speaking of interesting patterns, The three-body problem has led to the discovery of some truly mind-bending orbital configurations. There's the figure-8 orbit, where three equal-mass bodies chase each other around in a looping pattern, or the choreographies, where the bodies periodically return to their starting positions after executing complex dance-like motions. These special solutions are more than just mathematical curiosities. They've expanded our understanding of what's possible in celestial mechanics and opened up new avenues for exploring the dynamics of multi-body systems. They've even inspired new approaches to space exploration, like using chaotic orbits to navigate the solar system with minimal fuel consumption. The impact of the three-body problem goes far beyond celestial mechanics. It's been a driving force in the development of chaos theory, which has applications in fields as diverse as weather prediction, economics, and even the study of population dynamics in ecosystems. The three-body problem has also pushed us to develop new mathematical tools and ways of thinking about complex systems. It's a perfect example of how seemingly simple questions in physics can lead to profound mathematical insights. The work on this problem has spawned entire branches of mathematics, like dynamical systems theory and topology. And here's the mind-bending thought: the three-body problem might even have implications for our understanding of free will and determinism. If such a simple system of three bodies can produce behavior that's fundamentally unpredictable, what does that say about the much more complex system that is the human brain? But perhaps the most profound impact of the three-body problem is philosophical. It stands as a humbling reminder of the limits of human knowledge and predictability. In an age where we often expect science to have all the answers, the three-body problem shows us that there are still fundamental questions about the universe that we can't fully resolve. It's a testament to the depth and richness of even seemingly simple physical laws. Just three bodies interacting according to Newton's law of gravitation, a law we've understood for centuries, can produce behavior so complex that it stretches the limits of our mathematical abilities. Hey there, let's take a closer look at the three-body problem, a cosmic puzzle that has made its way into our stories and movies. One book that really stands out is Liu Cixin's The Three-Body Problem. It's more than just a sci-fi tale. It weaves together the science of the three-body problem with big ideas about humanity, technology, and the universe. In the book, we're thrown into a world where Earth gets caught up in the gravitational chaos of a distant star system. The story uses the three-body problem as a metaphor for the uncertainties and challenges of life. Just like the chaotic movements of stars, our fate is influenced by forces beyond our control. One of the coolest parts of the book is how it explores the fragility of our civilization. We meet a group of scientists who end up making contact with an alien race that's also facing a crisis. They live in a three-star system where the unpredictable gravity has caused their society to collapse. It's a parallel to our own struggle against nature and the consequences of our technological advancements. Throughout the narrative, Liu Cixin masterfully intertwines scientific concepts with profound philosophical questions. The three-body problem becomes a symbol for the unpredictability of progress and the potential for catastrophic consequences when civilizations collide. As readers follow the characters navigating this intricate web of science and ethics, they are forced to confront their own understanding of humanity's place in the universe. Are we doomed to repeat the mistakes of others, or can we harness our knowledge to forge a better future? The novel also touches on themes of trust, betrayal, and the ethical dilemmas that arise when faced with the unknown. As the characters grapple with the implications of their scientific discoveries, they are confronted with the moral questions surrounding contact with an alien civilization. This mirrors the very real debates we have today about the consequences of technological advancement and the responsibilities that come with it. What happens when scientific curiosity leads to unintended consequences? How do we balance our thirst for knowledge with the ethical implications of our actions? The impact of the three-body problem extends beyond its pages and has sparked a resurgence of interest in the scientific concepts it explores. From academic discussions to online communities, readers have been inspired to delve deeper into the intricacies of celestial mechanics and chaos theory. The novel has opened up a dialogue about the relationship between science and society, encouraging people to think critically about how we approach the unknown. But the three-body problem isn't the only cultural artifact that has been influenced by this cosmic conundrum. The idea of chaotic celestial mechanics has permeated various genres of storytelling, from films to video games. The unpredictability of the three-body problem serves as a rich source of inspiration for exploring themes of chaos, order, and the unknown in creative works. Sci-fi enthusiasts often find themselves captivated by stories that tackle the challenges posed by multiple celestial bodies, and the concept has become a staple in the genre. The allure of the three-body problem lies in its duality. It represents both the beauty and complexity of the universe. On one hand, it showcases the elegance of gravitational interactions and the intricate dance of celestial bodies. On the other, it serves as a reminder of the chaos that can arise from even the simplest systems. This duality resonates with audiences, inviting us to grapple with our understanding of the cosmos and our place within it. As we reflect on the cultural impact of the three-body problem, it's essential to recognize its role in sparking curiosity and inspiring future generations of scientists, writers, and thinkers. The interplay between science and storytelling has the power to captivate minds and ignite a passion for exploration. By weaving scientific concepts into engaging narratives, we can demystify complex ideas and inspire a sense of wonder about the universe. To close, the three-body problem is more than just a mathematical challenge. It's a profound reflection on the human experience. It serves as a reminder that the universe is filled with mysteries still waiting to be explored, and that our quest for knowledge is tied to the chaotic and unpredictable nature of existence. The three-body problem is like a puzzle that keeps popping up in books, movies, and even science. It's like the universe is daring us to figure it out, to embrace the mysteries we don't yet understand. And just like the stars and planets in the sky, we're all part of this big, beautiful cosmic dance. While this topic definitely is one to keep you fellows up at night, you can rest easy in the fact that these are the types of videos that I enjoy making. So I hope you did like it too. If our videos are right up your alley, let us know by leaving a like and subscribe so you don't miss anything we post. Until next time, stay insanely curious.